The second half of microbial cycle is regenerating sulfide in the process called anaerobic respiration, whereby oxidized inorganic sulfur compounds, mostly sulfate and elemental sulfur, serve as the electron acceptors with a large variety of electron donors, including fermentation products such as hydrogen, formate, volatile fatty acids, and alcohols, but also more recalcitrant organics like hydrocarbons. Sulfur-dependent disproportionation is basically in the same part of the cycle, despite the fact that part of the sulfur compounds is still ending as sulfate. It is because sulfur disproportionators are obligate anaerobes, and most of them are closely related to sulfate-respiring bacteria. Sulfidogenesis are mostly present in anaerobic sediments in aquatic habitats and are most active in marine systems rich in sulfate. They are often referred to as secondary anaerobes, since they are mostly utilizing products of fermentative or primary anaerobes, which hydrolyze polymers and ferment monomers. The sulfidogens, particularly sulfate-reducing, are divided into three groups: hydrogenotrophic, which are often called also autotrophic, fast-growing incomplete oxidizers, oxidizing volatile fatty acids and alcohols incompletely to acetate, and slowly growing complete oxidizers, oxidizing volatile fatty acids to CO2. Despite the fact that sulfate-reducing bacteria were known for more than a century, the complete understanding of their biochemical mechanism has only recently been finalized. Sulfate is a relatively chemically inert molecule. Therefore, the first step of its enzymatic reduction is activation using ATP and conversion into much more reactive sulfide, resulting in 2-electron reduction of the sulfur atom. The second step is reduction of sulfide to the final product sulfide by 6-electron reduction. It is a complex cascade with a multi-protein complex called DSR, dissimilatory sulfide reductase. The sulfate-reducing enzymes are located in the cytoplasm, but they are interacting with the membrane complexes, which are transferring electrons from the membrane menagenol pool. This combination results in outward protons translocation, and the created delta pH is used to produce ATP by the membrane ATP synthase. The mechanism of microbial elemental sulfur respiration is completely different from sulfate respiration, and in most cases such microorganisms cannot reduce sulfate and vice versa. The major problem with using elemental sulfur is that it is water insoluble. Therefore, the first step in this process is chelation into a soluble form performed by sulfur transferases containing terminal cysteine, which attacks sulfur ring and form a linear soluble organic polysulfide. This is transported to a periplasmic membrane anchored enzyme called polysulfide reductase, PSRABC, performing 2-electron reduction of sulfur atom to sulfide. The electrons are transferred to the catalytic subunit PSRA from the reduced quinol pool via membrane-associated PSRBC. This process results in proton gradient used by ATP synthase. In the reaction of sulfur disproportionation, one sulfur atom is oxidized to sulfate, providing 6 electrons to reduce the other 3 atoms to sulfide. This microbial process is truly unique and currently only known in a few obligatory anaerobic bacterial species. The main reason is that thermodynamically it would seem as the mission impossible. But the positive delta G can be overcome if the reduced product sulfide is constantly removed either by binding to added iron to form insoluble iron sulfide or by flushing out by a gas stream. This makes delta G slightly negative, barely enough to sustain a weak growth. From the basic enzymology point of view, the process is performed by a combination of periplasmic sulfur reduction by PSRABC in the reductive branch and the reversed sulfate reduction, whereby the DSR system works in reverse, performing 6-electron oxidation of zero-valence sulfur to sulfate.